Hello student, today we are going to discuss modeling of mechanical system. According to the motion of system, we are going to model this mechanical system. We are going to classify this mechanical system into two basic types. First one is translational mechanical system and second one is rotational mechanical system. Okay, so the translational mechanical system is related to force and translational motion. Okay, and the rotational mechanical system is related to torque and angular motion. So, to find the mathematical model of a mechanical system, we have to apply Newton's laws of motion. Okay. So, based on type of motion, mechanical systems are classified into two types. Okay. So, coming to translational mechanical system. Okay. So, this translational mechanical system move along a line, along a straight line. So, here the basic element of translational mechanical system. Okay, so these are the basic element of translational mechanical system. First one is translational spring, second one is translational mass, and third one is translational damper. Okay, so mass, spring and damper are the fundamental components of a mechanical translational system. The spring and the mass are energy storage element and the dashpot is an energy absorbing element. Now come to the first element. First element is translational spring. A translational spring is a mechanical element that can be deformed by an external force such that the deformation is directly proportional to the force applied to it. It stores energy during the variation of its shape due to elastic deformation resulting from the application of a force. When a force capital F is applied to the spring, a restoring force that is small f suffix k is produced, and this force depends on the stiffness constant k of the spring and the displacement x. Okay, so the restoring force Fk is equal to k into x. Okay, where Fk is force in Newton. This is restoring force which is expressed in Newton. Unit is Newton. K is the stiffness constant of spring, and this is in the unit of K is Newton per meter, and x is the displacement, and this displacement in meter. Okay, so by Newton's second law, the force, that means capital F, is equal to the restoring force, that means small f suffix k. So that's why this capital F applied force is equal to k into x. Okay, when the spring has displacement on both ends as shown in figure, then this restoring force Fk equal to k into x1 minus x2. So therefore the force from Newton's second law, the force, applied force F equal to restoring force, and this is equivalent to k into x1 minus x2. Okay, now the second element, now coming to the second element is translational mass. Okay, so translational mass is an inertia element. A mechanical system without mass does not exist. So mass is a mechanical element and it has inertia. Okay. So when a force capital F is applied to a mechanical body which mass is capital M and displacement takes place, and a reaction force small f suffix small m, this is reaction force, is generated in the body in the direction opposite to that of applied force, that is capital F. Okay. So the reaction force small f suffix small m is proportional to the acceleration A. So that's why this reaction force is proportional to acceleration, and so if we, and this proportional sign is represent, so this reaction force is proportional to acceleration and this reaction force is equal to F. If we eliminate this proportional sign, then we represent, then we have considered a constant. So here we consider the constant m. M is the mass. So this Fm equal to reaction force is equal to m into A, and this is equal to acceleration is nothing but a double derivative of displacement. So m equal to d2x dt2, which is represented by x double dot in this previous slide. Okay. So according to Newton's second law, the applied force is equal to this reaction force, and this is equivalent to m into d2x dt2. Okay. Now coming to third element. Third element is translational damper. Okay. So when the viscosity or drag is not negligible in a system, we often model them with the damping force. Okay. All the materials exhibit the property of damping to some extent. If damping in the system is not enough, then extra element like example dash pot are added to increase damping. Okay, so a viscous damper or dash pot is a mechanical element which is used to damp out unwanted vibration. Sometimes it is necessary to introduce damping to improve the dynamics of the system. Damping can be added to the system by using dashpot. Okay. So if a force is applied, to the shaft, that means here. Okay. So if a force is applied to the shaft, the piston moves and presses the fluid. Okay. This will increase the pressure inside the dashpot. Okay. So see if a force is applied to the shaft, means here this is shaft of the dashpot. Okay. So if a force is applied to the shaft, the piston moves. This is our piston. Okay. So piston moves and presses the fluid inside the dashpot. There is fluid is there. Okay. So if force is applied to the shaft, the piston moves and presses the fluid. Okay. This will increase the pressure on side B. This side is B, indicated by red arrow. Okay. And will decrease the pressure on side A. Okay. So as a result, the fluid flows around the piston from side B to side A. Okay. So if necessary, a small hole can be drilled through the piston to provide a path for the flow of fluid instead of the annular passage. Okay, so this is the working of dashpot. Okay, so see, an ideal dashpot with one end fixed, see the figure. Yeah. When a force F is applied, then the dashpot produce a reactive force which is represented by small f suffix b, and this is proportional to the velocity. So Fb proportional to the dx dt. This is the first derivative of displacement. The first derivative of displacement obviously is the velocity. Okay, so this Fb equal to, if we eliminate this proportional term, then we introduce one constant. So here we introduce one constant is b. Okay, so b actually b is the viscous friction coefficient. Okay, so Fb means Fb is reactive force. So this reactive force is equivalent to b into dx dt. Okay, so according to Newton's second law, applied force F equal to this reactive force. So that's why F equal to b into dx dt. Okay, so now when the dashpot has displacement at both ends as shown in figure, then this reactive force is equal to b into dx1 dt minus dx2 dt. Okay, so according to Newton's law, applied force capital F equal to this reactive force, and this force is equivalent to b equal to dx1 dt minus dx2 dt. Okay, to obtain, now how we will draw a free body diagram from a mechanical translational system. So now we will see how we will draw a free body diagram from a translational mechanical system. Okay, so to obtain the mathematical model of a mechanical system, it is necessary to draw a free body diagram indicating the various forces acting on it. Okay, in a free body diagram, each mass is considered separately with all forces acting on it. So what is the procedure to free body diagram? Actually, why we draw the free body diagram? Actually, we want to obtain the mathematical model of a mechanical system, because from this mathematical model we will calculate the transfer function of the system. Okay, so from this transfer function we analyze the behavior of the system. Okay, so from this mathematical model actually we analyze the behavior of the system. Okay, so what is the procedure to draw free body diagram? The first is assume the direction of displacement of the given mass as positive direction. Next, find all the forces and its direction acting on the mass. For example, force applied is in the direction of displacement, and the opposing forces due to spring, dashpot and mass are opposite to the direction of displacement. Then, using Newton's law of motion, express all the forces in terms of displacement or velocity of mass. Okay, so once the free body diagram is obtained, we can easily write the differential equation by equating the sum of applied force to the sum of opposing forces. Okay, so once we will find the differential equation of the mechanical system, then we can easily analyze the behavior of the mechanical system. We can easily find out the transfer function, input output relationship of this mechanical system. Okay, so take an example. Okay, so take an example of translational mechanical system. Okay, so this is our mechanical system. Okay, so see, from this mechanical system, how we will draw the free body diagram. Okay, so see, first step. So what is the first step? First step is consider the mass alone. Okay, so here we consider this mass. Consider the mass alone. Okay, second step is the applied force. That means this is our applied force, capital F. Applied force is in the direction of displacement. Okay, so the direction of displacement is this. So here applied force is apply in the direction of displacement. Okay, okay, this is our applied force. And the reaction forces due to spring, dashpot, mass oppose the displacement. Okay, so see, this is our restoring force. This is our restoring force. This is our reactive force, and this is our reaction force. Okay, so all these three forces are opposes the displacement, because our displacement in the direction of applied force, in this direction our displacement. So all the forces, that means reaction force, reactive force or restoring force, are opposes the direction of displacement, opposes the displacement. Okay, and only the applied force is in the direction of displacement. Okay, clear? Now represent all the forces in terms of displacement. That means here Fk, if we Fk is represent in terms of displacement, then this Fk equal to Kx. If we, and now come to the reaction force. Reaction force is Fm, small fm, and if we write this small fm in terms of displacement, then this is equal to Fm equal to m, capital M, into d2x dt2, and third one is our reactive force. Okay, so this reactive force, if we want to represent this reactive force in terms of displacement, then this Fb equal to capital B into dx dt. Okay, now by Newton's law of motion, algebraic sum of all forces is 0, or sum of applied forces is equal to the sum of opposite forces. Okay, that's why F equal to capital F equal to Fk plus Fm plus Fb. Okay, so this equation represent the dynamics of the mechanical of this mechanical translational system, and is called mathematical model of the system. Okay, now if we apply Laplace transform on both sides of this equation, considering all initial conditions 0, then that means if this Fk, Fm, Fb in terms of, if we write in terms of displacement, and then if we apply Laplace transform, then we find this equation. Okay, and this equation is the transfer function of this mechanical system. Okay, clear? Then I hope you people you people have understand how we will draw a free body diagram from a translational mechanical system, okay, and how we will find the transfer function of this mechanical system. Okay, so student, today I will stop here. Thank you.